That's how we discovered dark energy. At least, that's how the story begins. An extraordinary event sent shockwaves through both the astrophysics and particle physics communities. A sudden, intense burst of high-energy neutrinos recorded at CERN coincided almost perfectly with an anomalous transmission from NASA's Voyager 1 probe. One signal emerged from beneath the Earth's surface, from the world's most powerful particle accelerator. The other traveled billions of miles across interstellar space. That they occurred nearly simultaneously, within half a millisecond, was either a cosmic fluke or the sign of a hidden link between the quantum world and macroscopic systems spanning the universe. Was this synchronicity purely random, or were we seeing the first evidence of an undiscovered thread weaving subatomic events with deep space instrumentation? What follows is a journey through experimental techniques, theoretical frontiers, and the farthest reaches of our imagination as science attempts to answer that question. On March 22, 2025, at precisely 3 hours, 14 minutes, and 7 seconds Coordinated Universal Time, CERN's neutrino monitoring systems lit up with unprecedented activity. Dr. Elena Kowalski was the first to notice something unusual. We were conducting standard calibration procedures when the detectors went absolutely wild, she recalls. My first thought was that we had an equipment malfunction. But it wasn't a malfunction. A powerful burst lasting just 3.7 seconds registered across detectors at both the Large Hadron Collider and, thousands of kilometers away, at Italy's Gran Sasso laboratory. What made this event so puzzling was its signature, explains Dr. Rajiv Patel, lead neutrino physicist at CERN. Unlike the smooth energy curves we typically see from cosmic ray neutrinos or solar activity, this signal was sharp and distinct, with a pronounced peak around 2 tera-electron volts. The sheer number of interactions, over 120 within seconds, was unprecedented in neutrino astronomy. High-precision atomic clocks confirmed the exact timing of the event, a critical detail that would soon take on extraordinary significance. Meanwhile, at NASA's Jet Propulsion Laboratory in Pasadena, California, flight controller Sarah Chen was monitoring routine data from humanity's most distant explorer. Voyager 1 was behaving normally, or as normally as a 48-year-old spacecraft billions of miles from Earth can behave, Chen explains. Then suddenly, the carrier wave showed this bizarre modulation pattern unlike anything we'd seen before. NASA's Deep Space Network reported a strange fluctuation in Voyager 1's carrier wave. The timing, once adjusted for light-speed transmission delays, was identical to the neutrino burst at CERN. Dr. Marcus Brenner, head of NASA's Interstellar Mission Analysis Team, understood the implications immediately. Considering the spacecraft's radio signal takes nearly 20 hours to reach Earth, the timing suggested something profound. This wasn't a case of one event causing the other. Both phenomena appeared to originate from a shared mechanism, one capable of spanning astronomical distances and scales simultaneously. News of the dual anomalies spread rapidly through scientific circles. Within hours, emergency teleconferences connected researchers across time zones. Initially, there was a lot of skepticism, remembers Dr. Lena Anderson, theoretical physicist at Princeton University. Coincidences happen, even extraordinary ones. But as we examined the data more closely, the statistical improbability became increasingly difficult to ignore. The first task was to rule out conventional explanations. Teams worked around the clock to check for equipment errors, data processing glitches, or environmental factors that might have affected both systems. We considered everything from solar activity to seismic events, says Dr. Carlos Oliveira, who led the error analysis team. But nothing could explain both the neutrino spike and the spacecraft anomaly occurring in perfect synchronization. Within days, preliminary findings were shared with select governmental agencies. By the end of the week, a classified briefing was held at the White House, where officials from NASA, the Department of Energy, and the National Science Foundation presented what little they knew. The meeting was tense, recalls one anonymous attendee. When you tell world leaders that we may have witnessed something that fundamentally challenges our understanding of physics, they tend to ask uncomfortable questions about implications for national security. Theoretical models sprang up like wildfire in the weeks following the incident. The most radical proposal came from Dr. Yuki Tanaka at the Tokyo Institute of Quantum Gravity. What if Voyager 1's electronic subsystems were somehow quantumly entangled with particle interactions at CERN? Tanaka proposed in a controversial paper that it quickly became the most downloaded physics preprint of all time. In this interpretation, changes in one system would be mirrored in the other, not through signal transmission, but through fundamental quantum correlations that transcend space and time. Entanglement at such macroscopic scales would rewrite physics textbooks, explains Dr. Elizabeth Morris, quantum information specialist at MIT. Conventional theory suggests entanglement is fragile and difficult to maintain even in controlled laboratory conditions. The idea that it could persist across billions of miles and between such disparate systems seemed preposterous, and yet, the data pointed in that direction. Critics immediately highlighted the enormous challenges to this theory. For entanglement to persist at these distances and between such completely different systems would require some kind of quantum coherence preservation mechanism we've never observed before, argues Dr. Robert Chen of Caltech. It's an extraordinary claim requiring extraordinary evidence. Nevertheless, quantum labs worldwide began designing experiments to test whether electronic systems could indeed maintain entanglement correlations under conditions similar to those on Voyager. Another compelling theory emerged from the particle physics community. Dr. Fatima al-Zahrani of course proposed that the event might be evidence of sterile neutrinos, hypothetical particles that could interact with both known neutrinos and electronics via a dark sector field. Kindly like, share and subscribe our channel for further more updates about space.